Okay. Okay. So welcome everybody to our algebraic geometry seminar today. So today we are very happy to have Kenta Hajisume from Niigata University, and he's going to talk about minimal model theory for low canonical pairs and low canonical loci. Okay. So please, thank you.
Yeah, thank you very much for the introduction. And I thank the organizer of the seminar for opportunity to talk here. The title of this talk is the minimum model theory for low canonical pairs and low canonical loci. And I will start with very general talk of the bidirectional geometry and the minimum model theory. In the first section, I will introduce the notion of bidirectional geometry and the motivation of the minimum model theory. Next, I will explain the minimum model theory for log canonical pairs, and I introduce some known results. And finally, I will explain how to generalize the minimum model theory for log canonical pairs to general normal pairs. And I will explain my recent result on minimum model program for normal pairs. Okay, firstly, I will explain the notion of bidirectional equivalence and the motivation of minimum model theory. Okay, one of the main goals of the algebraic geometry is to classify all algebraic varieties. But in general, there are too many algebraic varieties. So it is impossible to classify all varieties in details. For example, let VI be the one-dimensional variety defined by the equation. Then the study of commutative ring shows that Vi is isomorphic to Vj if and only if I equals j. So even if one-dimensional affine variety case, there are many varieties. So to classify all algebraic varieties, we need another idea. One of the idea is to use the notion of isomorphic almost everywhere. Okay, I use the above example. We consider V prime I instead of Vi. Here, Vi prime is the set theoretically Vi prime is the Vi minus origin. Then Vi prime is defined by these two equalities in the three-dimensional complex space. Then we can directly check that this ring is isomorphic to this ring. We can directly construct C isomorphism between these rings. And this ring does not depend on I. This shows that VI prime isomorphic to Vj prime for all ij. And this ring corresponds to the algebraic variety defined by this equality. And this algebraic variety is punctured line. So this VI prime is isomorphic to punctured line. Okay, and this shows that VI is not isomorphic to Vj, but VI is isomorphic to Vj almost everywhere. Okay, this is notion of birational equivalence. Two algebraic varieties x and y are birationally equivalent if there exists Zariski open subsets U and V such that U is isomorphic to V. And this isomorphism is denoted by dot arrow, and this is called a birational map. Okay, in the previous example, the set of VI modulo isomorphism class has one-to-one correspondence to the set of natural number. On the other hand, the set of VI modulo birational equivalence class has one-to-one correspondence to one element. So, the number of birational equivalence class is drastically smaller than the isomorphism class of varieties. Okay, the motivation of the birational geometry is to classify is that all algebraic varieties can be classified by using birational equivalence. But there is a natural question: how to classify varieties? For the classification, we firstly find birational invariants. This is they are invariants. They are invariants not changed to birational modification. And then compute these birational invariants. And finally, we classify varieties based on these computation and geometrically properties of the varieties. The geometrical properties of varieties are also important for the classification. For example, the existence of rational curves in the variety are one of main topics of the birational geometry. And we often discuss that which type of vibrations do variety have. For example, when the variety have Calabi-Yar vibration or fan vibration, then we can classify varieties with these vibration structure. Currently, bilateral invariants behave where when we deal with projective varieties. So in general, we often deal with projective varieties. Here, projective variety is a closed subvariety embedded in the projective space. Yeah. And next, I will explain the motivation of the minimum model theory. Okay, bilateral invariants are also are important to study, but in general, it is difficult to compute bilateral invariants. So we need to find a variety with good geometrical properties in the bilateral equivalence class. Okay, currently, varieties with good geometrical property means that variety with good canonical divisor or canonical line bundle. For projective variety X, we may canonically define the canonical divisor. And the canonical divisor is often denoted by Kx. And this often corresponds to a canonical line bundle. For example, if suppose that X is non-singular. In this case, X is a complex manifold. Then canonical divisor is the divisor corresponding to the line bundle defined by this top rational form. So an important point is that the canonical divisor is defined only from the information of X. So the study of canonical divisor is almost equivalent to the study of the variety X. In the minimum level theory, property of Kx is very important. For example, positivity or negativity from viewpoint of intersection theory and the asymptotic behavior of this invariant is also important. Yeah, so this asymptotic behavior is called the Kodaira dimension. And in the bilateral geometry, some varieties are classified using the Kodaira dimension. Yeah, the goal of the minimum level theory is to construct a variety with a good canonical divisor. When we are given a projective variety with a good singularity, then we inductively construct a variety which is better than the original variety. Okay, from now on, I will explain the minimum model theory for smooth surface. Smooth surface case. Okay, let X be a non-singular projective surface. Then divisors of X are formal linear combinations of irreducible curves on X. Then we can define the bilinear pairing from the product of set of divisors to the to integers to the set of integers. This bilinear pairing is called intersection number. Okay, in general, the definition of the intersection number is difficult, but when the irreducible curves C1 and C2 on X intersecting transversally, then the intersection number of C1 and C2 is the number of points of the intersection. There is another approach of the intersection number from viewpoint of the topology. For every divisor on X, then there is a corresponding line bundle L on X. For example, C1 corresponds to a line bundle L. Then we can define the first Chern class of L. Then the intersection number of C1 and C2 is the pairing of the first Chern class and the second homology class defined by C2. Okay, we can define the notion of Neff divisor. The canonical divisor is Neff if and only if the intersection number of Kx with any curve is non-negative. The notion of Neff divisor can be generalized to the Q-quality divisor of higher dimensional varieties. Definition 1.3 is a generalization of the Neff divisor for higher dimensional varieties. The canonical divisor Kx of a projective variety X is Neff if and only if some multiple of Kx is Cartier. And the intersection number is non-negative for every curve. Yeah, now I will explain the construction of the minimum model program for smooth surface. We start with non-singular projective surface X. Yeah, firstly, we check that whether there is a curve E such that E is isomorphic to projective line and self-intersection number is -1. This is called the -1 curve. If such curve exists, then we can use the Castelnuovo's contraction theorem. By this theorem, there is a bilateral morphism F from X to a smooth surface X prime. Such that F E is contracted by F, and F is isomorphism outside E. Sorry, in this talk, non-singular is equivalent to smooth. Because we will work over the complex number field. Okay, now we get new smooth variety X prime. On the other hand, if there is no -1 curve on X, we stop the discussion. Okay, this is a first step of the minimum model program, MMP. Next, if there is a -1 curve on X prime, then we use the Castelnuovo's contraction theorem, and we get new smooth variety. In the second step, if there is no -1 curve, then we stop. Then we can repeat this discussion. And finally, we get smooth projective surface X tilde such that there is no -1 curve. This surface called minimal surface. Then explicit study of the geometry of the minimum surfaces, we know that X tilde has exactly one of the following structure. The property A is the nearness of the canonical divisor. Okay. When the canonical divisor is nef, we can classify X tilde by the Kodaira dimension. The structure A0 corresponds to the Kodaira dimension is 0. And the structure A1 is the Kodaira dimension is 1. And this is Kodaira dimension 2. The structure A0 is called Calabi-Yau variety in the weak sense. And the structure A1 is called elliptic fibrillation. And the structure A2 is called the variety, canonically polarized. Good minimum model with good minimum model of general type. So Kodaira dimension. A variety satisfying with this equation is called varieties of general type. So the structure A2 is minimal surface of general type. On the other hand, structure B is called ruled surface. There is a fibrillation to curve B such that fibers of the fibrillation is isomorphic to P1. And the final structure is that X tilde is isomorphic to the projective plane. The theory of minimum model program for smooth surfaces implies that if we are given a smooth projective surface, then by using the minimum model program and the classification of the structure, we can get the minimum surface X tilde having the structure of having one of the structure of these types. And this is one of good classification in the evolutionary equivalence class. So we want to generalize this result to higher dimensional varieties. Okay, this is a question toward the minimum model theory for higher dimensional varieties. But currently, this is incomplete. So the minimum model theory for higher dimensional varieties is incomplete. One of the difficulty is that we need to deal with we need to deal with worse singularity, but bad singularities. Okay, this is a rough statement of the conjecture of the minimum model theory. Okay. Suppose that we are given a projective variety with mild singularity. Yeah, I will explain the precise definition of mild singularity. Normal, log canonical singularity or over pair. Then we can construct inductive construction of bilateral maps, and we finally get good variety Xn. Yeah, this is a rough statement of the minimal model program. Okay, currently we often deal with pairs of varieties and divisor on it. This is because we want to carry out inductive argument on the dimension of varieties, and we want to use important result on the vibration called the canonical bundle formula. Yeah, to use this formula, we need to deal with the framework of pairs. Okay, this is general motivation of the bilateral geometry and the minimum model theory. So next, I start the minimum model theory for log canonical pairs. Okay, is there any question so far?
Any questions so far? No, I think so far so good.
Okay. So next, I will explain the minimum model program for log canonical pairs. Yeah, MMP means minimal model program. Okay, firstly, I define pairs. Okay, in this talk, all varieties are defined over the complex number field. Yeah, and from now on, all varieties are assumed to be a normal projective variety. Here, normal means the varieties with normal singularity. And let delta be an effective Q divisor on X. Here, effective Q divisor is formal rational combination of codimension one subvariety. And effective means that every coefficient are non-negative. Okay, then normal pair x delta is a pair of x and delta such that kx plus delta is Q Cartier. Here, kx plus delta is often called log canonical divisor. Okay, now I define the important invariant. This is called discrepancy. This invariant is important to define classes of singularities. Let x delta be a normal pair and we pick a prime divisor over x. And we take a projective bilateral morphism F on which E appears as a prime divisor. For example, we can take F as a resolution of X. Then we can define, this is the set of divisors on Y. Then we can write, we have this equality. And this is a divisor which represents the difference between ky and the pullback of the log canonical divisor. And the coefficients of E in the divisor is called the discrepancy of E. By using the discrepancies, we can define the counter log terminal pairs and log canonical pairs. Okay, a normal pair is called counter log terminal pairs or KLT pair for short. If the discrepancy is strictly greater than -1 for all prime divisor E. And a normal pair is called a log canonical pair or LC pair if the discrepancy is greater than or equal to -1 for all E. By definition, if x delta is KLT pair, then x delta is an LC pair. So the class of the category of LC pairs is larger than the category of KLT pairs. Okay, for example, let x delta be a pair such that x is smooth and delta is a simple normal crossing pair, simple normal crossing by divisor. Here, simple normal crossing divisor means that every component intersects transversally. Then the pair is KLT if and only if all the coefficients of delta are strictly less than 1. And x delta is LC if and only if all the coefficients are less than or equal to 1. Next, I define a step of minimum model program for pairs. Okay, a step of a minimum model program, MMP, is the diagram satisfying the four conditions. Here, x delta and x prime delta prime are pairs, and V is a normal projective variety. First condition is that F is birational, and F prime is birational and small. Here, small means that there is no exceptional divisor with respect to F prime. The second condition is that the birational transform of delta is equal to delta prime. The third condition is that entire log canonical divisor and the log canonical divisor are both ample over V, relatively ample. And the final condition is quite technical, but this shows that yes, the final condition is technical. Okay, roughly speaking, the third condition implies that F contracts every curve intersecting kx plus delta negatively. And after the contraction, this V this V may have bad singularity. So by using the partial resolution of singularity, we construct the new pair. Moreover, in the partial resolution of singularities, every extracted curve intersects the log canonical divisor positively. So F prime extract positive curves. So F contracts negative curves and F prime extract positive curves. And this is a diagram of MMP for pairs. I would like to remark that in this definition, these pairs are not necessarily log canonical. I defined the diagram for any pairs. Okay, this is these two conjectures are most important and fundamental conjectures in the minimum model theory. The first is existence of a good model. Okay, for a log canonical pair, then there exists a finite sequence of MMP such that the resulting pair is minimum model or modifiable space. Here, minimum model means that the log canonical divisor is F. And modifiable space is the structure of a special kind of fibrations. more precisely, there is a structure of the vibration such that the entire mechanical divisor is ample over the base, and the relative rank is 1. The vibration with this condition is called the fan vibration. So any modifiable space is a special kind of fan vibration. The second conjecture is the abundance conjecture. Abundance conjecture predicts the minimum model. The resulting minimum model is much better property. More precisely, the log-mechanical divisor is semi-ample. Here, semi-ample means that some multiple of this divisor is base point free. Okay, sorry, I have several remarks, but it is relatively not important. But the third remark is non-result. These two conjectures are known in the low dimensional case. For example, existence of a good minimum, good model is proved for LC pair such that dimension of X is not greater than 4. And the abundance conjecture is proved in the case of dimension not greater than 3. So the problem is the higher dimensional case. Okay, since I don't have enough time, so I will go to the KLT case. Okay, roughly speaking, currently there are the minimum model theory holds for some special cases. For the KLT case, we can always run a minimum model program. Let X delta be a KLT pair such that Kx plus delta is not nef. If Kx plus delta is nef, then X delta itself is a minimum model. So there is nothing to prove. So we only need to consider the non-nef case. Then we can always construct a step over MMP. Okay, to construct F, we need the special theorem called Kohn and contraction theorem. This theorem was proved by Kohn theorem was proved by Mori, and contraction theorem is a direct consequence of the Kawamata-Shockley base point free theorem. And the existence of F prime was proved by Biruka, Cassini, Heikon, and Makana about 10 years ago. Moreover, currently, these results are proved. For any KLT pair, the existence of a good model and the abundance conjecture hold for if X data satisfies the one of the following conditions. Delta is big, or the log canonical divisor is big, or the log canonical divisor is not pseudo effective. Here, not pseudo effectivity, non-pseudo effectivity means that for any ample divisor A, or any ample Q divisor, kx plus delta plus A is not big. As an important corollary, if a KLT pair whose if a KLT pair satisfies the condition that the log canonical divisor is not pseudo effective, then we can construct a finite sequence of MMP such that the resulting pair has the structure of a modifiable space. By construction of MMP, we see that all these pairs are KLT. So this is a KLT pair. Okay, another important corollary is that any Q factorial variety of phenotype is a Mori-Dream space. Yeah, here Mori-Dream space is an ideal variety from the viewpoint of minimum model theory. In other words, we can discuss minimum model theory for all divisors. This is they are important known result for the KLT case. And similar results are known for LC case. Okay, even in the case of LC case, we can always run minimum model program. In other words, we can always construct a step over MMP. Okay, let X delta be a LC pair such that the log canonical divisor is not an F. Then we can construct a step over MMP. Yeah, in the LC case, the cone and contraction theorem for LC pair was proved by Fujino. And the existence of F prime was proved by Bilka and Heikonshu independently. So these results are breakthroughs in the minimum level theory for log canonical pairs. Okay, after after these results are proved, Chen Fu and me proved the existence of a good model and partial generalization of the abundance conjecture. Okay, Fu and my results is that for any LC pair X delta, then the existence of a good model and the abundance conjecture hold for X delta if one of the following conditions holds. The first condition is that delta is the sum of an effective Q divisor and effective ample Q divisor. So delta is A plus B. Here A is ample. B is effective. Yeah, ample effective. Or if the log canonical divisor is not pseudo effective, then the conjecture 2.5 and 2.6 hold for this pair. And the direct corollary corresponds to the existence of a modifiable space for KLT pairs. Let X delta be a log canonical pair such that the log canonical divisor is not pseudo effective. Then we can construct a finite sequence of an MMP. And the resulting pair has the structure of a modifiable space. Here, by construction of MMP, we know that any pair in the MMP are all log canonical. Okay, so resulting pair is an LC pair. Okay, theorem 2.14 is an LC analog of the results by BCA, Bilka, Cassini, Heiko, Makana. Any Q factorial varieties of LC phenotype is a Mordorium space.
So excuse me. So in your statement of 2.12, so delta is sum of FT and ample. So isn't that does it mean that it's big? Or what's the difference between these terms?
In the in the now we cannot generalize this condition to the big case. So it is not known that conjecture 2.5 and 2.6 holds for LCX delta such that delta is big. And so this is a very huge gap between the bigness of delta and this condition.
And so can you remind us what's your definition of big?
Yeah. Okay. Yeah, delta is big if and only if this is very similar definition, but such that is ample effective, and this is effective. But the minimal model theory,
But in your statement, you
Oh.
need delta equal to ample plus or
yeah,
I see, I see.
yeah, this is equal to. So if sorry, if we replace delta to a prime plus b prime, then LC property may break. So x delta is LC, but x a prime plus b prime may not be LC. This is because we changed the Q linear equivalence.
I see. Thank you.
Yeah. In my result, we need to do the this condition plus log canonical property. This is a very very technical gap between this property and this property in the minimal theory. Okay, this is a known result for log canonical case and KLT case. Okay, in the final section, I will explain how to generalize these results to general normal pairs. Okay, is there another question? Is there another question?
Any more questions? Oh, okay, I think there's no more question at the moment. So.
Okay. Yeah. Finally, I will explain the MMP for normal pairs. Okay, let X delta be a normal pair, not necessarily log canonical. The main question of this section is the following. Does the minimum model theory hold for any normal pair? Okay, to give an affirmative answer, we need to prove the three facts. Firstly, we need to prove the existence of a step of MMP for any given normal pair. Secondly, we need to prove the existence of a minimum model or a modifiable space. Thirdly, we need to prove the abundance conjecture. Okay, these three statements are the goals for the minimum model theory for normal pairs. However, unfortunately, there exists counterexamples to each of the statements. So all these statements are not true in general. Okay, to check this, we firstly construct.
So excuse me. So when you say normal pair, then what's your condition on delta?
Delta is just effective Q divisor, just effective Q divisor. So there is no more condition.
Okay, so you don't assume the coefficient to be less than one. This.
Yes, less than one.
Okay.
Okay, so any some coefficients can be greater than one. Okay, now we construct a surface, a special surface. Let E be an elliptic curve with embedding to a projective space by a very ample clarity divisor H. And let X be a projective bundle over E by constructing with this rank 2 vector bundle. And let S be a unique section of this global section. Yeah. By the standard argument, we can check that we have this relation between divisors. And we can construct a contraction of S. Contraction morphism S of S. This shows that X so pi S is a point and pi is an isomorphism outside S. Okay, finally, let D be a numerically trivial non-Trojan divisor. So any multiple of D cannot be trivial divisor. Okay, then this is big. This divisor is big. So we can find the effective divisor. So now we have X, S, and B, and F, X to E, and pi, X to Z. Okay, now I construct the counterexample to the previous three statement. The counterexample to the first statement is a pair. Yeah, here the quotient of S is 2, so greater than 1. Yeah, this is a proof, but yeah, this is directly direct consequence of the construction. Roughly speaking, pi and f are possible non-trivial contraction morphism. And S is the unique kx plus 2s plus b negative curve. So pi is only contraction morphism of kx plus 2s plus b negative curve. However, there is no diagram over MMP. Indeed, if such diagram exists, then phi prime is small. So x prime is isomorphic to z because x prime and z are surfaces. However, kx prime plus 2s prime plus b prime is not Q-Cartier. This is because D is non-torsion. Yeah, we need a technical discussion to show the non-Q-Cartier property. But this is not difficult. Okay, the counterexample to the second statement is also this pair. Yeah, the following is the proof. Since this divisor is Q-linear equivalent to this divisor, and this is pseudo-effective. So by the property of the minimum model program or the modifiable space, we can check that this pair cannot have a modifiable space. Moreover, we cannot construct a step over MMP. So this pair does not have a minimum model. So this pair does not have a minimum model or a modifiable space. Yeah, more strongly, we can prove that there is no bilateral morphism such that the push forward of the divisor is nef. So this is because f and pi are all possible non-trivial contraction morphism. And we have checked that file, which was this that is not Q-Cartier. And this morphism is not birational. Yeah, so this pair is a counterexample to the second statement. In the final, the counterexample to the third statement, abundance conjecture, is the pair. Okay, by construction, we have this relation. And since D is numerically trivial, so Kx plus S plus B is NEF. But by construction, D is not a torsion. So for any M, this multiple is cannot be trivial. So if this divisor is semi-ample, then some multiple have to be linearly equivalent to zero. So we get a contradiction. So this divisor is not semi-ample. Okay, so these three examples are counter examples to all statements of the minimum model theory. Okay, such bad property is due to the existence of S. More precisely, S satisfies the conditions that the discrepancy of this S with respect to this pair is strictly less than -1. And there is a curve. There is a curve C contained in S. In other words, C equals S, such that the self-intersection number is negative. Yeah, this shows that the intersection number of this kx plus 2s plus b and s is negative. So this shows that there exists kx plus 2s plus b negative curve contained in the non-LC locus. Okay, here is a definition of non-LC locus. But since I don't have enough time, so I will skip this definition. The important thing is that the set theoretically non-LC locus is the union of all centers of prime divisor E such that the discrepancy is strictly less than -1. So we recall that X delta is LC if and only if this discrepancy is greater than or equal to -1. Yeah, so this is a set of points on which X delta is not logarithmical. Okay, I will introduce technical theorem to run a minimum model program for normal pairs. This is a Kohn and contraction theorem for normal pairs. This is proved by Fujino. Okay, and this is a construction of steps of an MMP for normal pairs. Okay, yeah, by this theorem, we can construct the left side part of step of MMP. In a special situation. Okay, and by using this theorem, we can construct the whole diagram of a step of an MMP. Okay, so sorry, I will skip the proof. But we can construct this diagram locally. Okay, anyway, I will skip the proof. Okay, now I explain how to run MMP for a special normal pair. Okay, let X delta be a normal pair, and suppose that for any curve C, if C intersects the non-LC locus, then intersection number is non-negative. This is a special condition for the normal pair. For example, the stable base locus, suppose that the stable base locus of the log canonical divisor is disjoint from non-LC locus. This is this is the intersection number, intersection of such D, support of such D. Yeah, anyway, this is, we assume the special condition. If kx plus delta is nef, there is nothing to prove because x delta itself is a minimum model. So we may assume that the log canonical divisor is not nef. Then we apply the Fujino's command contraction theorem, and we get morphism F such that F contracts kx plus delta negative curve. Okay. Then we can use the condition. Since kx plus delta negative car is disjoint from non-LC locus, then F is isomorphism around the non-LC locus. Then we can use the next theorem. Next theorem for the construction of MMP of step. So MMP step. Then we can construct a step over MMP. First step over MMP. Now, suppose that x prime delta prime also satisfies the condition star asterisk. Then by the same argument, we can construct a next step of an MMP. We can repeat this argument or the construction of an MMP as long as we can produce pairs x two prime delta prime such that the condition asterisk holds. For example, suppose that the log chemical divisor is pseudo effective and the stable base locus is disjoint from the non-LC locus. Then we can construct a sequence of steps of an MMP. In other words, if we construct the first step of an MMP, then x prime delta prime also holds this condition. X prime delta prime also satisfies this condition. So we can construct next step of MMP. And this pair also satisfies the condition. So we can construct the third step of MMP. And we can repeat these constructions. Okay, so this is a question of MMP for normal pairs. Suppose that if x delta satisfies this condition, then we can construct a finite sequence of an MMP such that kx plus delta is nef. Okay, finally, I will introduce my main result. Okay, suppose that all minimum level program for KLT pairs terminate. Then we can give affirmative answer to the question 3.8. And question 3.8 holds when delta is the sum of effective amplitude divisor, sum of an effective amplitude divisor and an effective divisor. This is a generalization of foo and me. Result of foo and me. Let x delta be a normal pair such that delta is an effective amplitude divisor and effective divisor. And suppose that x delta satisfies the following condition. Then we can construct a finite sequence of an MMP such that the resulting pair satisfies the semi-ampleness of the canonical divisor. Okay, this is my recent result. Okay, I'll stop here. Sorry for the speedy talk at the final part. Thank you very much.
Thank you very much. So are there any questions or comment? Yeah, so I'm wondering that in Fujino's cone theorem, then the summation is a finite sum or could be infinity of the negative extreme rays.
Yes, when if the delta is A plus B such that A is ample, then the number of J is finite. This is proved in the Fujino's paper.
Okay.
But I don't know. But we don't know any property of this part.
Okay, but then in your setting of the MMP for normal pair, you kind of avoid this part.
Yes. In my result, in my result, this MMP does not modify around non-LC locus. So this is MMP along the log canonical locus. I forgot to the name of this MMP.
Okay. And also, so what's the main differences between the MMP for KOT pairs and MMP for LC pairs?
Yeah. Yeah, in the KLT case, we can easy to change the boundary part delta. But in the log canonical case, it is very difficult to change the boundary part because LC property is very delicate to deal with. So many argument in the KLT case cannot be applied to the LC case. So MMP for LC pairs is much more difficult than the MMP for KLT pairs.
Yeah, so basically we need to be more careful about the boundary part in the LC case.
Yeah, exactly. Yeah. So this is a reason we can only prove the MMP for LC case in this setting. Yeah, this is a main difference between the MMP for LC pairs and MMP for KLT pairs.
Okay, yeah, thank you.
Yeah.
And any other questions? Okay, so if not this thing, Hajisume again, yeah, thank you very much.
Thank you very much.
Okay, so that's the end of today's seminar. And next Friday, we're going to have Ziwei. Yeah, and Ziwei Zhang is going to talk about something about tropical geometry. Yeah. Okay, thank you.
Okay. Thank you. Oh.